So now that we're familiar with our node voltage method, let's look at some more examples, starting with this bridge circuit example. And so this might be a circuit that you've seen before, and so you might recall that we can't combine these resistors easily with parallel and series combinations, but if we wanted to do resistor combination techniques, we'd actually have to do delta to Y transformation and work from there. So it's oftentimes going to be easier to just do node voltage or mesh current as opposed to doing all of that work to do a delta to Y transformation. Not that it's crazy difficult, but a little more straightforward. And so let's say in this particular circuit, what we're trying to find is the power dissipated in our 20 ohm resistor. So find our power dissipated in our 20 ohm resistor. And so remember, we know that resistors are always going to dissipate power. So if we go through steps 1 and 2, remember step 1 is identifying all of our essential nodes and determining a reference node. So of course here we have 3 elements connected. We have our 50 volt source, so we could draw that really all of this coming here and here is going to be one single essential node, or we could just mark it as this point. Similar thing over here, all of this is going to be one node, but we can just mark it right there. We have another essential node here because we have 3 resistors connected. And then of course this whole bottom part and here, which we can again just mark as right here. So in this case, all 4 of these nodes are essential nodes. So all nodes are essential nodes. And we have 4 of them, so we know that n sub e is equal to 4. And we're going to be looking for 4 minus 1, which is 3 equations. And we don't have to do this little bit here, but that can just kind of be a useful thing to do as you're planning your way through this solution. So as I work through this one, I'm going to skip some of the steps that we wrote out explicitly in terms of the KCL and our Ohm's law, but this could be a good opportunity to, of course, pause the video, work through it yourself. If you feel like you need some of those extra steps, by all means, please still include them. This is only the second problem we're working with this technique, so I don't expect you to be proficient in it just yet. But like I said, I'm not going to write it out explicitly this time around. But I'm happy to do it if anybody has questions and wants to see it in more detail later on. So we've identified our essential nodes, so now we're going to choose our reference node. In this case, all of the essential nodes have 3 elements connected, so we don't have an obvious choice in terms of one having a lot of things connected, so that should be our reference node. Usually, just out of habit, I'll make this bottom one our reference node, just because we're kind of used to seeing the negative polarities on bottom. There's no reason that you should not choose any of the other 3. Any node is going to be a decent choice in this one. Well, let me take that back. Actually, 2 of them are going to be better choices, and we'll talk about that when we get into our next video as to why that is. Okay, so we've defined our reference node as being the bottom. So let's go ahead and say this is node 1, this is node 2, this is node 3. So we see negative at our reference node. So for instance, this is going to be V3, this is going to be V2, and now we know our V1 is also going to be negative, but let's just come over here because all of this is the same node, remember? So we can put a negative over here, and at the top, all of this is the same node, so we can put a positive over here, and that's going to be V1. Okay, so now we're ready to write our 3 node voltage equations. So let's start with node 1. So for node 1, we could come here and we could start by writing all of our currents leaving this node. We could say, all right, we have 1 here, 1 coming out here, 1 coming out here. We could go through a similar process to what we did with the last example to get our currents through these resistors. But notice we run into an issue when we're talking about this current going through the voltage source that's by itself. And that's because we don't have anything like Ohm's law that applies to our ideal sources. So this 50 volt source is going to output 50 volts whether it is sourcing 1 amp or 20 amps. So it's an ideal source. The same way you might think of a frictionless surface in a physics class. Fortunately, however, one side of this 50 volt source is our reference node, so we don't actually have to define this current, but instead all we have to say is that V1 is equal to 50 volts. And so we can see that pretty clearly how I've drawn it here as well, that node voltage V1 is simply equal to the value of that source. Again, this would have been an issue if one of these was not the reference node, and we'll come back to that, of course, in a later example to talk about how do we deal with that if one of those two was not a reference node. Okay, but for now we sort of got an easy node 1 equation. All right, so let's move on to our second one, node 2. So we can kind of use that form that I had written in the last video, which was basically if we're interested in a current, it's V of interest minus V adjacent divided by R connecting them. So if we follow that, what we can say at this node 2 is our current going out the top, our node of interest is V2, our voltage at our node of interest is V2, minus our adjacent node, which would be V1, divided by resistance connecting them, which is 12 ohms. Same thing for our current going out the right through the 10 ohm resistor. Voltage at our node of interest is V2, minus our adjacent voltage, which is V3, divided by resistor connecting them, which is 10. Same thing for current going out the bottom. We have voltage at the node of interest is V2, and we could explicitly write that our voltage at the reference is 0, or we could just leave it as V2, either way, and we divide that by the resistance connecting them, which is 0. That's all of our currents. We set that equal to 0. So we see we've just sort of bypassed having to write the KCL equation explicitly and having to come back through with Ohm's law and KVL to get it in terms of node voltages. If you're not comfortable with skipping that, again, by all means, feel free to do that. But as you become more comfortable, hopefully you'll be able to do this sort of quicker way. Okay, so another thing I'm going to do a little differently with this problem is I'm going to collect these terms from this equation, but I'm not going to get rid of the denominators. So for instance, let's say we have this V1 term from our first term, so I'm going to multiply, we have negative 1/12 times V1. Now, from each of the three terms, we have a V2 component. We have 1/12 V2 plus 1/10 V2 plus 1/6, all of that times V2. And then from our second component, our second term, we have this minus 1/10 times V3. So why in the world would you want to do this and not get rid of those fractions? Well, maybe you don't, but the reason I like to do it is it avoids me making some stupid math error along the way as I'm simplifying. But by all means, not something you have to do. This is just a personal preference thing. One thing I will notice how I put our minus signs inside here instead of having, for instance, a minus 1/10 V3. And that's just, again, to kind of help me from making any mistake. That way I know that coefficient is minus 1/10 and I don't accidentally put positive 1/10. Okay, so there's our node 2 equation. So this is our node 2 equation. So now let's move on to our third and final equation, node 3. So we can do a similar thing using this sort of simple formula here, or if you'd like to write out the KCL and Ohm's law for each one, by all means do that as well. If we're talking about the current going up through that 4 ohm resistor, we have voltage at node of interest V3 minus adjacent, which is V1, divided by resistor connecting them, which is 4 ohms. So 4 ohms. Current going out the left through the 10 ohm resistor is going to be V3 minus V2 divided by 10. And then finally, current going out the bottom is just going to be V3 over 20. All of that is equal to 0. So again, I'm just going to collect terms without getting rid of the fractions. So from the first term, we have a minus 1/4 times V1 From the second term, we have plus a negative 1/10 times V2. Again, I'm being careful with that negative sign and my coefficients. And then we have a V3 term in each of the three terms, so 1/4 plus 1/10 plus 1/20 times V3. All of that equals to 0. So here is our node 3 equation. So at this point, we have our 3 equations and 3 unknowns. Given that we have this V1 equals 50, we could pretty easily substitute that into our other 2 equations and solve for 2 equations and 2 unknowns. But maybe we have 6 equations or 5 equations, and we don't want to risk making math mistakes. So what I'm going to show you is how we can easily just plug that in using our matrix method. So we would have V1, V2, V3, so that's our variable matrix, and that's going to be equal to. So now for our first row in our coefficient matrix, it comes from our node 1 equation. And so I can rearrange this, or not necessarily rearrange, but I could rewrite this and say that this is really just V1 plus 0 V2 plus 0 V3 equals 50. And so using that in the first row, of course my coefficients are then 1, 0, and 0. And this matrix is ultimately going to be inverted. So now from node 2, we have negative 1/12, that whole mess in the middle, and then negative 1/10. So just copying that down here, I have negative 1/12. I have for our second term 1/12 plus 1/10 plus 1/6. And then our term being multiplied by V3 is negative 1/10. And then finally, from our node 3 equation, we get our third row of our coefficient matrix to be negative 1/4, negative 1/10, and we get 1/4 plus 1/10 plus 1/20. And then our constant matrix is just 50 from our node 1 equation and zeros for the other ones because we did not have any other sources. If we plug that into our calculator or Octave or MATLAB, we get V1 is 50 volts. Of course, we already knew that. V2 is 22.44, and V3 is 36.86. Because all of our entries were in ohms and amps, that means that our final result is going to be in units of volts. Okay, but remember, we were asked about the power dissipated in the 20 ohm resistor. So we have to go to step 5 in our process in order to calculate that power. So remember, if we're talking about a resistor, we actually have 3 forms we can use. We can use our traditional IV, we can use I squared R, and we can use V squared over R. Depending on what's available, one form might be more attractive. In this case, we already have the voltage across this resistor, V3, and of course we know the resistance R, so we can just use our V squared divided by R form. So we can say power in our 20 ohm resistor is equal to V3 squared divided by R. So plugging in, we see right here, we got that our V3 was approximately 36.86 volts. Square that, divide by our 20 ohms, and we get that this is approximately 67.93 watts. So that would be our final answer. One thing to note is, of course, 67.93 watts is a whole lot of power for a little resistor. The typical resistors that we'll deal with in the lab are usually half watt or quarter watt rated. So that means they can handle up to 0.25 or 0.5 watts. Some of them might be able to go all the way up to 1 watt. But 67 watts is a whole lot of wattage for one resistor. And the reason for that is typically in these starter problems, the numbers are such that they work out easily in the calculations and they're not necessarily realistic values for circuits. Okay, so in future lectures we're going to look at a couple other examples and a couple other concepts with our node voltage, but hopefully you're becoming more comfortable. But like always, please let me know if you have any questions.